Good morning. Okay, if you've read my comments on the assessment intro, you'll know that we're kind of treading water a little bit today. I don't want to push on too quickly with polar coordinates. I want the basics to bed in for you before we move on to look at the area and the tangent stuff. However, I have attached the notes for the second part of polar coordinates for you to have a little look at, absorb, read, before we come together and look at it next week. And that's going to be our focus next week. Just to let you know what I'm thinking about it. Our plan after that is to then move on and look at de Moivre's theorem, which is a complex number based topic, which is the next thing we need to do on the course. Once we've done that, we will be, I'd say, pretty much halfway through the course, the Unit 4 course. Obviously, we've got a lot of consolidation to do when we get back in September, but I'm confident that we can have most things covered by Christmas and then have a nice long sort of time to bed it all in before the summer. Our main thrust next term will be the other module that we're doing, which I think I'm right in saying at the moment is likely to be Unit 6, the mechanics module. But we'll talk more about that later. Okay, so if we're treading water, what are we doing? Well, we're going to practice some curve sketching today. Polar coordinate curve sketching, which you saw a little bit of an introduction to if you read the notes for last lesson. I don't think there was much of it in the exercise as such, and I'm not going to use the integral exercise for this. I'm going to use an exercise from the AQA book, which I've attached to this lesson. So I'm going to do a couple of ones first, and then basically the way I do these is similar to how you're going to do them from the worksheet. There are two very important points I'm going to make when I do these sketches, well, this one specifically. So please make sure you do keep listening to this video, because it's really, really a very, very important point that I'm going to make. Sounds exciting, doesn't it? It's not really that exciting. Okay, so r equals 5 cos 2 theta. So if I want to plot that, the best thing to do is get my calculator out. I'm going to work in degrees on my calculator. So it says in radians, but it doesn't really make much difference. I could do it in radians. I just have to set my steps to be pi over 15 or something like that. Pi over 15, pi over 10, I don't know, something like that. Whereas if I do it in degrees, I can do my steps in 15 degree steps or something like that. So anyway, God, I'm babbling today. I'm going to go into table mode, and f of x, that's like r equals, so it's going to be 5 cos 2 theta, so 5 cos 2 x, like so. I mean, you could all do this all by hand if you really want to, but it'll take you a long time. Get my calculator to be a bit brighter if I put it over there. Yeah, that's better, isn't it? You can see that better now. So, don't need a g of x for this one. Okay, so start's going to be 0, end's going to be 360. I know it says minus pi to pi on here, but it doesn't really make any difference when it comes to actually getting the sketch. I know what I mean by 0 to 360 in terms of where I'm going to actually plot the points. Steps, I'm going to suggest 15 is a good amount to split them up. And here we go. Right, okay. So, a couple of points about the graph paper I'm going to use. This graph paper has already got numbers along here. I've given you a slightly different version of polar graph paper, which doesn't have the numbers along here. I've done it for a very good reason, and that's because very often the sketches that they want you to do don't have a number here. They have a letter instead, like A or something like that. And what you want to do in that case is, well, once you've established what the highest value is in terms of A, you can then put your own scale on it so that you can make the diagram a decent size. For example, I mean, on my diagram, if I'd have just done r equals cos 2 theta using this, it would have been really small down here. Okay, so to get around that problem, yours doesn't have a scale on it. You choose a scale based on what's appropriate for the question. Okay, to put that polar graph paper is attached to the video as well. Right, so anyway, here we go. So I can make my important point now. Right, so I'm going to start to plot the point. So 5 is 0, 15 degrees is 4.3. So 1, 2, 3, 4.3. It's only a sketch. It doesn't have to be perfect. Now 30 is 2.5. So 1, 2, 2.5. 45 is 0, which is here. Okay, so that's the first little section of my graph, and I can pretty much see now that it looks something like this. There we go. In that section of the graph. So that's the first 45 degrees. Now, once I go past 45 degrees, you will notice that the values go negative. And this is where I'm going to make my important point. Some people would tell you now, it's not wrong what they're telling you, it's just this is how the convention for something is, if it's a negative, you go the opposite direction to the direction the angle suggests you go in. So according to this one, 60 degrees would be in this direction, so I've got to go in this direction and plot a point 2.5, i.e. here where I've got my pen pointing now. Plot a point there. Here's the news, and it's really important. On our course, you do not do that. If you see a negative value of r, you don't plot it at all. So what that means is we're going to have a kind of a dead zone, if you like, round here, where nothing's going to happen until I get a value of 0 again. And that value of 0 doesn't occur until I get to 135 degrees. So at 135 degrees, between 45 and 135, nothing gets plotted at all. So I continue on now. So 135 is kind of on the origin. 150 is 2.5. You see these numbers are just the same as the ones before. 165 is 4.3. And then 180 is 5, which is there. 1, 2, 3, 4, there. Okay, and if I plot that little section, it looks like that. Okay, so if I keep going, you can probably work out what's going to happen next. So the next one is 4.3, then I get me 2.5. This is there. Then I get me 0, which is, oh, I messed that up. No, I haven't. 225 is 0, so that's that one there. So it comes round, something like that. And, well, it's presumably now going to go negative again for a dead zone down here. And that dead zone won't finish until I get to 315 degrees, which is here. At which point it's going to do something similar. It's going to go out at 330 to 2.5, which is there. And then at 345 it's going to go out to 4.3, which is kind of there. And I'm going to join it up. And I'm going to get this kind of propeller shape here like that. So that is what 5 cos 2 theta looks like to us. Now here's the important bit. If you were to go onto Desmos and type in r equals 5 cos 2 theta, you would get 2 rogue petals. You would get a petal down here like that and a petal up here like that. As far as we're concerned, they do not exist. And this is why it is so important that you needed to hear that fact that I just told you about the fact that when r is negative, we simply do not plot. So you can tell where r is negative, where you get a sort of a dead section. So if you were travelling out from you were on a journey from the origin, decided to go on a journey. If on your journey you happen not to have passed you don't go over the curve, you don't cross over the curve, then you're in a dead zone, and that means that the r value would have been negative for that value of theta. I hope that's clear. Second important point is to do with tangents at the origin. So what I mean by this is, here, if I draw the line called a half line, theta equals 45 degrees, that's theta equals 45 degrees, or pi over 4, it is a tangent to the curve at the origin. Okay, this is going to become really important when we start to look at areas. So whenever r equals 0, so that's not the only tangent on this graph, there's one for each of the values where r was 0. So there'll be one at 315, there'll be one at 135, and there'll be one at 225, like that. So these are called tangents to the curve at the origin, and they will become very important when we start to look at finding the area of the curve. Right, let's have a look at the other one then. R equals 4 sec theta. I put this one on because it's quite a nice one to show you. So again, I'll do mine from 0 to 2 pi this time. It doesn't really matter. So f of x equals 4 sec theta from 0 to 2 pi. Let's have a look at this one here. So 4 sec, which I can't do on here because there isn't a sec function. Well, actually, there probably is, actually. I don't know, do you get it in the options? No, you don't. You just get the hyperbolic functions in there, do you? Alright, anyway. So there's no sec theta on here, so I manufacture it by writing it as 1 over cos. So it's 4 divided by cos x, like so. And I'm going to do the same things as I did before, 0 to 316 steps of 15, and here are my values. Okay, so you'll like this one. Okay, so here we go. So at 0 it's 4, it is here. At 15 degrees it's 4.1, so it's a little bit more than 4. So here's 4, but I'm going to go a little bit further out, just a smack, just a snippet further out. 30 degrees is 4.6, so that's just past there, right about there, like that. Can you see what's happening? At 60 degrees, it's 8, which is pretty much off the end of my scale, but I can just about get him in. So here we go, 60 degrees, 1, 2, 3, 4, 5, 6, 7, 8 is kind of there, and then 75 degrees, 15, it's off the top of my page, you can't see it, but I'm up here somewhere. Okay, at 15 degrees. Okay, so they're all positive. Oh, 90 degrees is an error. Interesting. But once I go past there, they're negative, so I don't plot them. So I don't plot anything in this section here at all. Desmos would plot it. Okay, it wouldn't actually cause a problem in this case. I wonder if you can see why, if I think about that. But it does sometimes cause a problem. But Desmos would have plotted all those, and it wouldn't have caused a problem. See if you can see why. But sometimes it does. But we don't plot them. Okay, so they're negative all the way around to 270, which is an error. And then 300 is 8, so 300 is kind of there. A little bit less than that, sort of there. 315 is 5.6, which is 1, 2, 3, 4, 5 and a bit there. Okay, and did I miss out doing 45? Did I get carried away and I didn't do 45? I did on a 5.6. I didn't plot it, did I? Oh dear. Anyway, 5.6 is there. There we go. I missed it out earlier. Thought there was a big jump to 8. That was silly. Right, where is he? So then we're going to get 345 at 4. Hang on. I haven't done that one ever. 330 at 4.6. I think you get the idea now, aren't you? Shall I just shut up and just... Right, anyway, there we are. There's the points that you get for r equals 4 sec theta, which if I join up, make a straight line. Okay, they make a straight line. Now, just to finish, this will not hopefully be much of a surprise for you, because if I had have asked you to change that into its Cartesian version, you would first of all have written it as r equals 4 over cos theta, like so. You would then have rewritten it as r cos theta equals 4, like that, and then you would have consulted the formula that we did last lesson and noticed that x equals r cos theta was our way of converting between, one of our ways of converting between polar and Cartesian. So you'd replace that with x and you get x equals 4. I wonder if you can work out what would be there if you wanted a horizontal line rather than a vertical line. I'll leave you to think about that. That's me done. Have a go at the curve sketching. Enjoy. See you next time.